In the last section, I showed you how to work out the atmospheric pressure at a given altitude in an isothermal layer. In this section, we're going to move it on a bit, and I'll show you how to derive the expression so you can work out the pressure at any altitude in layers where the temperatures change a bit, but particularly where there's a constant lapse rate. So, at the start of the lecture, I showed you that in some parts of the atmosphere, the temperature decreases with altitude, but the atmospheric pressure must always decrease as altitude increases. But the air temperature can change, and sometimes you might have a positive lapse rate, and sometimes you might have a negative lapse rate. And this has to be taken into account when calculating the atmospheric pressure at any particular altitude. And we can do this if in constant lapse rate layers, remember the lapse rate is lambda, where there's a linear relationship between the air temperature and the altitude. So lambda we can define as the change in temperature with the change in altitude, and again this is minus, so if the temperature is decreasing with increase in altitude, then this is positive. Okay, so that's the equation we have from the previous slide, and we can rearrange this to make dz the subject. So we've got our change in temperature over the lapse rate, and if you remember from the other section, we got the hydrostatic equation, pressure equals rho gh, and instead of using h we put in altitude, and we got to this expression. Okay, so the change in pressure equals to minus rho g change in altitude. We now have an expression for altitude in terms of the lapse rate. So if we substitute that into here, okay, we end up with this new expression. And we also showed that the density is also related to the pressure and temperature from the ideal gas laws. And so again, go back and look at how I did that, remembering that R in this instance is the specific gas constant and not the universal gas constant. So if we substitute rho into this equation, we now have this expression where we've got the change in pressure is equal to pressure times gravity over RT times by the change in temperature with respect to the lapse rate. So we can rearrange this and integrate it now. So if we again bring the p down here, rearrange it, then we have the integration of 1 over p between p0, and remembering that the subscript 0 in all these calculations relate to the bottom of the layer that you're interested in. So if the layer that you're interested in is the bottom layer in your atmosphere, then the bottom of the bottom layer is the ground. Okay, so this would just be sea level conditions. But if you were interested in an altitude that was in, say, the third layer in your atmosphere, then the bottom of the third layer is the top of the second layer. So that's the conditions that you should be using for that particular example. So can we return into this? So if we integrate between the bottom of our layer and the pressure we're interested in, and again integrating between the temperature of the bottom layer and the temperature that we're interested in, then if you run through this integral, and I recommend you do it just to prove it to yourself, then you end up with this relationship. Okay, so we have natural log of the pressure at our altitude divided by the reference pressure times this constant times the natural log of the temperature that we're interested in over our reference temperature. And if we rearrange that, then we end up with this relationship. Okay, so now if we know the pressure at a given altitude, so if we know the temperature at a given altitude, we can now work out the pressure at that altitude given the base conditions as well. However, we might not actually know the temperature at a given altitude, but we know that in a constant lapse rate area, layer, we can work out the temperature, because if we know the altitude, we can work out the temperature from the lapse rate. So the temperature at a given altitude would be equal to the temperature at the bottom of the layer minus the lapse rate times by the change in altitude between the altitude that you're interested in and again the altitude at the bottom of the layer. So substituting T into this equation gives you this. So this is our final equation for a scenario where you don't know what the temperature is, but you know the altitude and the lapse rate. So the ratio in pressure between pressure that you want and the pressure at the bottom of the layer is given by this expression here. And in the same way that we develop this relationship for pressure, we can use a similar analysis or similar method to get the ratio of the density ratio at your given altitude. And they're extremely similar, but just notice when you do it, you end up with another -1 in this power. Okay, so in this lecture we've derived quite a few formulae, kind of 6 to be exact. And so just a word of warning really, you just need to be quite clear which equation you're using for which type of problem. So if you remember, we're kind of start over here. So the equations over here we developed for an isothermal layer, okay? So the temperature isn't changing with altitude, it's the same temperature. So we don't need to know what the temperature is at our given altitude because it's the same as the temperature at the base of the layer. So we can just use this expression for pressure and this one for density. Okay, so these two are for isothermal layers. If we have, if we're in a constant lapse rate layer and we know what the temperature is, then we can use these two expressions, okay, because we're given the temperature, we know it, and also the lapse rate is in there, so we can work it out, okay. And then finally, if we're in a layer, a constant lapse rate layer, but we don't know what the temperature is at the altitude that we're interested in, then we can work it out from the lapse rate. So you use these two expressions here. So, or you could just kind of, work out the temperature from this equation and plug into here. But either way it would work. Okay, so you just need to be a little bit clear about which equations you're using for which type of layer. Okay, so that concludes this lecture on the atmosphere. Thanks for listening.